Hello, my name is Razvan Pascanu and I'm a research scientist at DeepMind. Let me first start by thanking the organizers for inviting me to give this talk. Today, I wanted to discuss continual learning in the robotics context. In particular, I want to ask what can we expect from merging these two topics. In the second half of the talk, Mikhail will provide a concrete example of a benchmark that we worked together jointly with Maciej, Lukasz, and Piotr, which could be beneficial or at least act as an additional starting point to study this question. Okay, let's jump directly into it. I wanted to start by first highlighting the definition of continual learning, or CL. CL is often defined by a protocol one has to follow. There's a sequence of tasks, and they have to be learned one after the other. Additionally, one also specifies what to expect from the solution, and this is usually given as a laundry list. That list includes things like the system should not suffer from catastrophic forgetting, meaning that learning a new task should not make you forget the previous ones. The system should be of fixed size or have a bound on the amount of computation it can use at training or at inference. Another item on the list is maximizing forward and backwards transfer or maintaining plasticity. Particularly on maintaining plasticity, I wanted to give a shout out to these papers as it is a much more subtle constraint which wasn't explored that much in the past. What works like Ash and Adam show is that under a sequential learning process, it's not only important to check the speed at which we converge on the new task or whether we can fully minimize the training error on the new task, but also if the generalization on the new task is affected even when you allow to train for as long as you want. While all three issues are covered by the term forward transfer, there is a lot of value in separating the three instances apart as they tend to have different causes and solutions. Ash and Adams provide evidence that in some scenarios, systems lose plasticity, where on the new task, your generalization ability is impaired, no matter how much training you do. Eagle et al. Explored this observation in the RL setting, and particularly in the continuous control context, while the work of Tudor Berariu and others further expand the empirical evidence and propose a hypothesis of what might be happening under the hood. While our understanding of this phenomena is still limited and it is not clear how much of an impact it might have, I thought it is useful to highlight as it can show the subtleties of what can go wrong under a continual learning regime. Coming back to the overall definition. Another issue, unfortunately, is that in practice, neither the protocol nor the requirements for a solution are really fixed or unique. We can see a lot of variations and variants of continual learning protocols. This is because continual learning is phrased in terms of competing objectives that require certain trade-offs to be made. And unfortunately, these trade-offs do not only depend on what we are hoping to achieve, but also on the domain and data that we use. To summarize this in one sentence, there is no one continual learning problem, but rather a collection of problems or of settings, neither less important or less realistic. And we don't yet have a full taxonomy of what CL might be. That means that every time we explore a CL setting, we need to be explicit about what form of continual learning we are exploring and why. For example, if we are to focus on forward transfer, some traditional setups for CL might not even allow us to study this question. What would one expect to transfer among permuted MNIST variants or Atari games? This is not to say that we might not observe transfer, but rather that it might be very hard to know if we are doing well, explicitly to know what an upper bound or target transfer should look like. And also if what we are transferring or what makes this transfer work will also happen in a different scenario, like for example in robotics. We either need to understand the relationship or similarity between the task given the model, something I would argue we still do not have the right tools to describe or investigate, or we need to already work on tasks and data similar to the one we care about that has the right kind of relationship and poses the right kind of issues to us to deal with. Also, as I hinted before, the transfer or even forgetting can depend on architecture and optimization choice. For example, in these two papers by Iman Merdad and colleagues, they showed that model size and optimizer can have a significant impact on the amount of forgetting or for transfer, meaning that a CL solution might look more or less sufficient to solve the problem depending on the architecture you might be using. And the choice of model optimization, the amount of overparameterization you can afford, and so on, are again defined by the data and the domain you are working on. So we need to be aware that we cannot easily isolate the continual learning problem from the data or the model so that we can treat it in vitro and come up with a generic solution that will naturally work everywhere. So what do we aim to fix by having a system that is able to continually learn? In a more generic sense, not thinking of robotics for a second, there are many different potential answers. For example, we know that humans cannot learn in an ID fashion. So we can think of continual learning as trying to understand the relationship and discrepancy between machine learning and human learning. Or it could be about keeping some large system, think about a chatbot, up to date without wasting a lot of compute. In what follows, I want to focus on a few themes that I think are relevant for the robotics context, but that also view continual learning a bit differently from the way we've been looking at it in the past couple of years. In particular, I want to move away from catastrophic forgetting as the main goal. While it has its very real application, and for example, it can be crucial to maintain safety protocols in a deployed robotics system, particularly those kind of safety protocols that have to be learned, I think there are other aspects of continual learning that have been somewhat overlooked. One important issue in robotics is efficiency of learning. Data is scarce and is very expensive. There are different aspects to this, but for now, I just want to look at the data efficiency of training a neural network, which tends to be the function approximator of choice for encoding a policy. Neural networks, while being the best performing systems we have, they tend to be very data intensive. Part of it is because of the learning process itself, which relies on a tug of war dynamics where each observation is pulling on the weights, and the solution comes from finding an equilibrium between these forces. This means that even if you learn how to act in a particular instance while learning how to act somewhere else, you have to rehearse what you already know, otherwise, you will catastrophically forget. And intensively rehearsing the exact same observation can lead to overfitting or discovery of very brittle correlation. One can view CL as being about finding an alternative way of doing credit assignment or blame assignment on the weights of the neural network, a way that could lead to considerable efficiency computationally, but also in terms of data used. Something that will allow knowledge composition at any level of the learning process, hence making the use of neural networks in settings like robotics more easy. Another way to think about continual learning could be to help when thinking about the OOD generalization question. This is becoming an important problem and is definitely of interest for any robotic system that one might want to deploy. The world keeps evolving, hence the training regime will never be fully representative of the observation that the system will have to deal with a deployment. Therefore, the learned system needs to generalize the data out of the training distribution. But if you are not thinking about it in a traditional static sense, where you have training data and testing data, but just as a system that learns with every observation that it receives, OOD generalization changes its meaning. There is no training distribution to be OOD with respect to. OOD generalization turns more into a tracking question of how quickly can the system incorporate new information and how quickly can it learn to act in situations it never seen before. Of course, it doesn't mean that there's no problem anymore, but at least the perspective is changed into one I believe might be a bit more tractable, where the focus is on speed of learning rather than generalizing to distributions you don't know much about at training time. Finally, one can talk about skill acquisition, which is a standard theme in robotics. This can also be seen as a continual learning problem where we want a robotic system to collect behaviors as it interacts with the world and to be able to meaningfully use them in the future to learn faster or to perform well. But again, it might require a different focus from other ways of thinking about continual learning. In the data efficiency perspective, for example, we'd be worried about how the learning happens at the update rule level. And we would think about a monolithic system. Here, we might not approach the problem in the same way. Model capacity might not be seen as a big worry, and forgetting can be solved by just storing copies of the trained model on the different parts of the data. The bigger issue is how to search through these skills and use or compose them. Particularly if we are to take exploration into account, which is something we really have to, we might have to deal with sparse rewards where we might not have a lot of signal to know whether we've picked the right skill at the right time. So on my last slide, I want you to draw a few conclusions based on everything I've said so far. There are multiple potential goals that can drive us towards continual learning, even within the robotic setting. There is things like data and computational efficiency angle. There's a changing perspective it might bring on the OOD generalization question. There is a hope of acquiring skills over time. CL solutions can be seen as a safeguard to maintain safety protocols, particularly those that need to be learned. There's no doubt in my mind that even partial solutions to continual learning can have a big impact on robot learning. However, it is also likely that continual learning is not one problem. It has a multitude of facets which stress different aspects of the problem differently. We really need to have a full taxonomy of continual learning, and I'm proposing here that maybe starting with the question of what a solution to this problem meant to help us with can be a way of start building that taxonomy. I have to also say that there's been previous efforts in building such taxonomies, which are extremely useful, but I would argue that we still don't have a complete set of all the different aspects of continual learning. There are some common themes as well for these different perspectives. For example, the goal of reusing acquired knowledge to learn more efficiently on new data can be seen as a common theme for all the three views that I've provided. Does that mean that we can collapse them into a single set of constraints into a single problem? And does that mean that there is one size fits all solution that will be optimal to address and deliver all of these goals? On that part, I'm not that sure, and I'm leaning towards no. Or at least there might be a solution unique to a unique solution for all of them. But if we are to care only of one or a few of these goals, we might be better off if we're looking for something specific, which might end up performing better than the one size fits all solution to all the different perspectives of continual learning. Therefore, I do think that having this taxonomy is very important, and I do think that we need to build many more benchmarks than the ones that we have to target these different goals and help us navigate the different facets of continual learning. These benchmarks need to be as close as possible to the real problem we want to solve, as data and model plays a big role. And on that note, I want to leave you to hear about the recent benchmark we've done that Michal will introduce. While this benchmark will not cover all the different issues I've mentioned, I believe it can be seen as a step forward. Thank you so much for listening.
Hi, everyone. My name is Michał Zając, and I'm really happy to be able to present here at this workshop. I want to start with a question that Razvan asked in the previous part, which is, what problems could we solve using continual learning? I want to argue that at least part of the answer is robotic control. So why robotics? First of all, it is an important and pragmatic real-world area that we all care about. Secondly, the domain of data that we train our algorithms on really matters. For example, if we design our algorithms working only with simple benchmarks, like, for example, split and mist, we cannot be sure that our solutions will generalize to more complex problems. Also, robotics is a natural domain to study knowledge reuse. By this, we mean how effectively can we leverage previous tasks to learn a new task. This is because in robotics, we can have diverse yet interconnected tasks. So with this in mind, we wanted to design a new benchmark that will allow us to measure progress in continual learning. I want to talk a bit about our motivation. So first, we wanted to study what happens at the intersection of continual learning and reinforcement learning. This is somewhat under-researched, and in particular, there is currently no widely accepted benchmark. We also wanted to focus on more realistic tasks than current CL benchmarks. Another interesting point is that we wanted to move past studying just catastrophic forgetting, and we want to emphasize that forward transfer is also a very important metric, and we will elaborate on this point later on. Also, our big hope is that a new benchmark could be like a lens through which we can see new interesting phenomena. So our starting point was Metaworld, which is a robotic benchmark, which is focused on meta-learning and multitask learning. So first, it is robotic-based, which is relevant to real-world problems. It has interesting inter-task relationships with potential for meaningful transfer. Also, the goals are externally defined and widely accepted by the community. It has interpretable metrics, which means that the success is well defined. And finally, it can be trained from state representation, which reduces the requirements in terms of computational power. In particular, we run all our experiments on just CPUs. We can also mention here that this all bases on MuJoCo, which is physics simulation engine, and it has recently been made available for free. So now everyone can use it. We name our benchmark Continual World. So this benchmark is a suite of robotic tasks, which comes together with evaluations of different continual learning methods. And our main test bed is dubbed CW20, and it is a sequence of 10 tasks, which is repeated twice. We evaluate methods from 3 broad classes of continual learning methods. The first one is generalization-based methods. In these methods, parameters of the model are restricted to stay close to those of previous version of the model, and this is done by adding some auxiliary laws. In replay-based methods, part of the data from previous tasks is saved and then periodically is used again in the training. In modularity-based methods, parameters corresponding to different tasks are separated so they don't interfere with each other. We included several metrics in our evaluations. First is average performance, which is just the mean success rate on all the tasks at the end of the training. Another one is forgetting, which is mean difference between performance at the end of training a given task and performance at the end of whole training. And this is averaged over all tasks. Last one is forward transfer. To compute forward transfer for a given task, we look at training curves when learning a task in sequence versus learning the same task from scratch. This is visualized in the plot on the right. Integral of the difference between those plots expresses how much more efficient is learning when we have knowledge from previous tasks. This integral, properly normalized and averaged over tasks, is our forward transfer metric. We want to especially emphasize the importance of this forward transfer metric. First, it is a great tool to study knowledge reuse because it just expresses how much knowledge from previous tasks help us develop a better solution to the current problem. This metric has been slightly neglected in the literature so far. And the important point is that most of the current continual learning methods really struggle with it. So even most of the methods are beaten by the simple fine-tuning baseline. In order to study forward transfer more deeply, we look at transfer between pairs of different tasks. We can measure the similarity of any 2 tasks by training them in a sequence and measuring the obtained forward transfer. This way, we can build a matrix representing the training dynamics between different tasks in the benchmark. We use it to better understand the tasks and their relationships. Sometimes pre-training on a different task helps, but other times it also can be harmful. Then we use this matrix to construct a longer, challenging sequence of tasks, which can be used to pinpoint some particular problems. So for example, one of those problems could be a Destructor problem, and we will elaborate on this later on. So our big hope here was that the new benchmark could help us see some new phenomena which are harder to see with simpler tasks. Also, it is worth mentioning that because our benchmark is relatively lightweight, we were able to run a lot of experiments and verify our all hypotheses. Also, we tested 7 different continual learning methods, and each experiment is run with at least 20 different random seeds to reduce the variability inherent in reinforcement learning experiments. So in total, we were able to run above 50,000 experiments. So now let's comment on some of the results. First of all, PACnet outperforms other methods by a wide margin. It is even better than multitask learning. This is very surprising because, for example, in supervised learning, multitask solution is treated as an upper bound. Also, PACnet is the only method with good both average performance and forward transfer metric. But this method still has its own limitations. For example, task boundaries needs to be well defined and known to us. And also we need to know number of tasks beforehand. Another point is that experience replay methods perform poorly, and this is in stark contrast to the supervised learning setup. And methods that reduce forgetting often have poor forward transfer. And even when some task is revisited, often there is no forward transfer or very poor forward transfer visible. Additionally, we were able to identify some unique challenges in terms of combining continual learning and reinforcement learning. In our experiments, we use soft actor critic, which is an actor critic algorithm. So in principle, we have 2 options. We can either regularize with continual learning methods both actor and critic, or we can regularize only actor. This is because in the final evaluation, only actor is needed to make decisions. So in principle, we can have forgetful critic. Empirically, we find that using continual learning methods only on actor and not on the critic gives better results. However, this is somewhat controversial because, for example, when we revisit some task, then the critic in practice needs to be learned almost from scratch here. Another issue is data being too off policy. We know that off policy data poses a challenge in general in reinforcement learning, and the distribution shift problem is even exacerbated in our setup because of frequently changing tasks. Finally, exploration in the continual learning setup is an important open problem. Choosing an exploration policy from a previous task could improve the results significantly. On the other hand, a poorly chosen exploration policy could degrade results severely. Another issue is so-called Destructor problem. Here we examine toy problems consisting of triplets of tasks. We examine sequences of tasks A, B, C, where the sequence A to C exhibits high transfer, and there is low transfer from B to C. And we are interested in the final performance on the task C. So ideally, we would expect continual learning methods to perform well here and be able to remember and reuse information from task A, whether there is task B in the middle or not. However, in practice, they fail and they are outperformed even by a simple fine-tuning, which forgets about the task A. We conclude that continual learning methods can often remember the past, but cannot efficiently reuse it. Another issue is about relearning a task. In CW20 sequence, 10 tasks are first learned and then revisited. And to our surprise, on a second visit, the metrics are much worse. So this may be due to reduced plasticity of the neural networks, or this may also be connected to problems with exploration. Here, it would be specific to the continual learning plus reinforcement learning setup. So what are the next steps? We want to provide here a short list of problems which we think are important and are highlighted by our benchmark. And we would be very happy to see some progress on these problems in the coming months. So one of them is developing methods with good forward transfer, especially when the destructor tasks are present. Also, important point would be to be able to quickly relearn a task. And another thing would be to propose methods which match PackNet performance, but have less limitations. So if you are interested in our experiments and benchmark, we encourage you to read our paper to find more experiments and more analysis. And we also have a website, and we have a leaderboard of different methods. This is called Continual World Challenge, and we encourage you to submit your own solutions to the leaderboard. So finally, I want to show the links to the website and to the GitHub, where there is the repository with the codes with all our experiments. You can also contact us about the benchmark or related stuff. So feel free to send us any questions. And thank you very much.